Okay, today we're going to be looking at power. So, excuse me. To make circuits work, we need to supply them with enough energy. So we need to know how much energy a circuit needs per second. This quantity of energy per second that the circuit needs is what we call power. And it is measured in watts, named after James Watt. So power is the energy required per second by the circuit. So 1 watt is equal to 1 joule per second. Now, we know that the potential difference is measured in volts, where 1 volt is equal to 1 joule per coulomb. So the voltage is 1 joule per coulomb. So it's like the energy required to per coulomb of charge. And we know that 1 amp is equal to 1 coulomb per second. So if we multiply these together, we get joules per coulomb times coulombs per second, which is joules per second, which is what we've defined power as. So this is our power. So we have found that power is worked out by current times voltage. Let's apply this to a simple circuit. So the voltage is 10 volts, the current is 600 milliamps, and we don't know the resistance. But because power is current times voltage, we don't need the resistance to work out the power of this circuit. We have 600 times 10 to the minus 3 times 10, which gives us 6 watts. Now, we can use, let's rewrite our equation. P equals IV. Now let's think, we also know that voltage equals IR. So if we substitute this in, we get power can also be worked out as I squared R. So that we can, if we don't know the voltage but we do know resistance, we can still work out the power. Also, current is equal to voltage over resistance. So P is also equal to V squared over R. So we've got this family of equations for power. Power is IV I squared R or V squared R. Now, if you don't want to memorise 3 equations, you know this one, you'll know this one, and you can use this to derive the other 2. But it's just useful to kind of be able to pull these different equations out. Now, we're going to look at different circuits, and from everything that we've learned so far, we want to be able to determine the resistance of any component. We want to find the potential across sections, current in branches, and the power, either for the whole circuit or for an individual component. So these are the types of questions that you would be required to answer in an exam. And to be able to answer them, you really need to be able to break them down into smaller chunks. Let's look at a circuit that we're going to analyse and find the values of all the different parts of. So we've got an ammeter here, and that reads the current is 0.1 amps. This means to be A1. This one a bit bigger so you can see it. Here's a resistor, 50 ohms. This is some other resistor which we don't know. And we have 82.5 ohms. And this voltage is 8.25 volts. And then we have another voltmeter, and we don't know the value here. So, firstly, we want to find, this is what we want to find. We want to find A, the potential across the parallel section. We want to find A1 and A2. We want to find the resistance R. I'll put a wee question mark here. Don't know which one it is. R question mark. We also want to find the total power. So that's all the pieces of information we want. So let's start off with A. So this part here is the simplest part for us to begin with, because we know the current, and we can think of this part here, we can consider this as going to be dealt with as, you could combine these two resistors to have one resistor, and then you've got a series circuit, and the current is the same in the whole of the series circuit. So we also know that the voltage is shared between, in a series circuit, is going to be shared between this part and this part. So we can then work out the voltage first, because that's going to be the easiest part to do. So we know that the supply voltage is equal to V1 plus V2, where the supply is 12 volts, V1 is what we want, plus 8.25, so the voltage will be 3.75 volts. So in these questions you need to go back and really understand how different the parallel and the series circuits, and how they deal with voltage and current differently, and how the resistances work. B, this resistance. Now, we know that the current Oh, no, we're in resistance. We're doing A1 and A2. Right, we know the resistance here and we now know the voltage. So the voltage is 3.75 volts. We know that the resistance here is 50 ohms, so we can use V equals IR to give us a current of 0.075 amps. So that is A1. So that's the current in 1. Now the total current in the circuit is equal to 0.1 amp. So that must be shared between these two branches, which must be equal to I1 plus I2. So that's 0.075 plus I2. So I2 must be 0.1 minus 0.075, which gives us a current of 0.025 amps or 25 milliamps. Then C, we want the resistance. So here we can use V equals IR. We know the voltage is 3.75. We now know the current is 0.025, and then we just need the resistance. So the resistance would work out at 150 ohms. And finally, for the total power, we use our equation P equals IV, where I is 0.1 and V is 12. So that's going to be 0.1 times 12, which gives us 1.2 watts. Let's do another question with a circuit that looks a wee bit simpler. So this time is 4.5 volts. We've got an ammeter here reading 75 milliamps. We've got a resistor and we've got a lamp. So the lamp requires 1.2 volts to work, but must not reach more than 4 volts or it'll be damaged. The resistance of the lamp is 10 ohms. Calculate the value of the resistor Does the lamp have the required potential? And finally, redesign the circuit so the lamp brightness can be altered easily. suggest values for the components. Okay, so part 1. Calculate the value of the resistor here. So we're going to be using our old favourite equation, V equals IR. We know the voltage is 4.5. We know the current is 75 milliamps. So it's minus 3 times R. So R is 4.5 over 75 times 10 to the minus 3, which is 60 ohms. We know the resistance of the lamp is 10, and it's in series, so the total resistance adds up. So total resistance, So R1 is equal to RT minus R lamp. So this is the value of the resistance in the whole circuit. So R1, which we'll call this R1, is going to be the total resistance, which is 60, minus 10, which is, this has got 10 ohms. So that's going to be 50 ohms. Does the lamp have the required potential? So now we can use Ohm's law again to calculate the potential over here. So the current's the same, but now we're going to use the resistance in the lamp. So I is 75 times 10 to the minus 3. The resistance is 10, so the voltage is 0.75 volts. So what were we told? It must have 1.2. So the potential is too low. So redesign the circuit so the brightness can be altered, and we want to suggest values for the that would work. Okay, so I'm going to remove this part and just keep the original drawing up. If we want to alter the potential across the lamp, we need to be able to vary the resistance here. The best way to do that is with a variable resistor. So let's draw that in. Turn this into a variable resistor. The question asks that we must consider the values that we want. So the lowest potential that the lamp can have is 1.2, and the greatest is 4 volts. Well, we don't want to actually no more than 4, so we'll use 3.99 volts. So we can use these values to calculate the maximum and minimum value of the resistor. So we'll use the potential divider equation. So we know that, which we had from before, which was V1 equals R1 over R1 plus R2 times Vs. And so we'll call this component is going to be component, this is the resistor is component 1 and the lamp is going to be component 2. So this potential lowest is going to be V2 min and this will be V2 max. And our supply voltage Vs is 4.5 and our resistor and R2 is 10 ohms. We can't change the resistance of the lamp. So let's do V2 max first is equal to R2 over R1 plus R2 times Vs. So that's 3.99, 10 over R1 plus 10 times 4.5. So then we're going to get 3.99 R1 plus 10 equals 45 times 10 times that, which gives us R1 plus 10 is equal to 45 over 3.99, which is 11.28. So R1 would be 1.28 ohms. So that is for the maximum limit. Then if we would repeat it for the minimum, so R2 min, R2 over R1 plus R2 times Vs. Oh, this is for, that's V1, so we're doing V, so yeah, change those numbers over. And then we would have run out of space. I'm not going to do, the working out is exactly the same. So we end up with R1 as 27.5 ohms. And that would give you the minimum value for the lamp to work. So this would be our new circuit diagram, and we would have a range of, so the resistance would be between 1.28 and 27.50 for the circuit to work. So hope that helps.